Good evening. Something very interesting is going to happen on the evening of May the 30th. There's going to be a partial eclipse of the sun, visible from all over the British Isles. And I'll give you all details about that and how to watch it right at the end of the program. Meanwhile, I wonder if you've noticed that very bright star high up in the north after sunset. It's called Arcturus, in Boötes the herdsman. And you can find it very easily by using Ursa Major, the Great Bear, which is now practically overhead. Simply follow round the bear's tail and you'll come to Arcturus, which you can't really miss, partly because it is so brilliant and partly because it's a lovely light orange colour. And I'd like you to compare that with another bright star in the northeast, Vega in Lyra the Lyre, one of the three members of the Summer Triangle, the others being Deneb in Cygnus and Altair in Aquila. Now, Vega's an interesting star. It was one of those studied last year by the Infrared Astronomical Satellite, IRAS, and found to be associated with material which may or may not be a planetary system in the process of formation. We don't know. Anyway, there it is, and Vega is blue, and the blue colour contrasts very strongly with the orange of Arcturus. Now, blue heat is hotter than orange heat, and therefore Vega is hotter than Arcturus. But they are made up of the same elements, hydrogen, helium and the rest, with hydrogen much more plentiful than anything else. Now, the stars, obviously, come from somewhere. And when we consider the origin of the universe, we are on very much less certain ground. I think it's now generally accepted that the universe began in what we call a Big Bang, something like 15,000 million years ago, and we could work out an evolutionary sequence from that. But the heavy elements are there, and we've got to decide how they were formed. And now there seems to be a general consensus of opinion that the more complicated elements, the heavier ones, were actually cooked inside stars. And this is where I'm delighted to welcome back an old friend of ours, Dr. John Beckman of Queen Mary College. Welcome back to the program, John. Hello, first of all, what do we really know about the Big Bang?
We are learning more and more about the Big Bang from astronomical observations. But perhaps more interesting still, we are learning more and more about the Big Bang too from particle physics. In fact, it isn't quite clear whether the physicists who are interested in elementary particles are teaching the cosmologists more at this moment or vice versa. You see, in the first few seconds of the universe, very near its origin, the average energy of the particles was extremely high, very, very high, much higher than the energies of particles produced in the biggest accelerators here on Earth, such as the one at CERN. And in fact, the Big Bang is sometimes nicknamed, for that reason, the poor man's accelerator.
Well, I think everyone's heard of CERN in Geneva. It's the French name for the Centre of European Nuclear Research. But there are still some people who regard it as a rather mysterious kind of device. What exactly does CERN do, John?
Well, very briefly, the physicists at CERN use their huge machine, which lives in a big tunnel more than a mile across, to accelerate particles to very, very, very high energies, cause one particle to collide with another, and from the resulting products to learn about the nature of the particles themselves and also about the fundamental nature of the forces interacting between them.
And this, in turn, gives us a clue as to how the various chemical elements were actually made.
Yes, I think it would be truer to say that the previous generation's high-energy physics gave us the idea about how the elements are made, particularly in stars. In the 1930s, when nuclear physics was first becoming well understood, people began to understand also how nuclear physics could be applied to producing the energies of the stars. In the middle of a star, such as the sun, the temperature is very high, the pressure is very high. Under those circumstances, hydrogen can fuse to form helium and release energy. In particular, hydrogen, 4 protons, 4 hydrogen nuclei can come together to form a single helium nucleus and release a gamma ray. And it's that gamma ray which gives the energy of the sun and effectively supports it. Now, these same nuclear physicists were able to show, very simply, that this process produces elements. Helium is one, and others. And they could show that hydrogen would be the most abundant element in the universe, with helium coming second, and then all the others a long way behind.
Well, of course, helium was actually detected in the sun spectroscopically more than 100 years ago now, before it was found on Earth. Well, it sounds all right, but things aren't quite so straightforward as that, are they?
Unfortunately, they're not. You see, if you do the sums and work out how much helium there ought to be in the universe produced in stars, it turns out that that result is 4 or 5%. But when you make the measurement, you find that the measurement gives actually nearer 30% by mass.
That seems to lead us back to the concept of the Big Bang.
Yes, because George Gamow, whose idea gave rise to theories of the Big Bang, he produced this idea in 1940 precisely in order to explain that discrepancy, in order to explain why there is too much helium in the universe. Although he proposed this theory, the hot Big Bang theory, in 1940, it wasn't taken seriously for another 25 years.
I never met George Gamow, and frankly I very much wish I had, because I gather he was quite a character in many ways.
I think he could be justly described as an eccentric.
Yes.
In fact, he was known to be a great physicist. He was considered so by all his contemporaries, but some of his more daring ideas had difficulty in being accepted. I think a little anecdote will illustrate both sides of his character. He was invited to a conference on stars. At that conference was one of his research students, Vera Rubin, who actually told me the anecdote a couple of years ago. And she describes how during the discussions on star clusters, he slept. He slept throughout the meeting. And in fact, he could be heard snoring all over the conference hall. Nevertheless, 2 days later, the organizer of the conference, Alan Sandage, received in the post a telegram describing a new way of measuring the ages of star clusters. And in fact, that new way, this new idea of Gamow, is the basis of all our present methods of measuring ages of clusters. In fact, the way it works is that he realized that the most massive stars are also, and the brightest stars are the blue stars. And such stars go through their fuel, hydrogen, very, very quickly, and then disappear, they explode normally. So if you see a cluster which has blue stars in it, it must be very young. Otherwise they'd have gone away.
Yes, indeed.
Well, young, say a million or a few million years. And then if you look at another cluster which has white stars as its brightest stars, that must be somewhat older, tens of millions of years. If you look at a cluster with yellow stars, perhaps hundreds of millions of years. And a cluster which has red stars as its brightest may be several thousand millions of years old. Now, this method has been refined considerably as we understand more and more about stellar evolution, but the idea and the working out of the idea was originally due to Gamow. It only goes to show that Gamow, while half asleep, was a clearer thinker than most of us wide awake.
Well, that wasn't all he did by any means around about that time, was it? He also predicted this background radiation, the weak radiation coming from all directions in the universe of a very low temperature now, which is probably all that's left of the last echoes of the original Big Bang.
This, too, was a natural product of his theory of the Big Bang, but it told against him, because it wasn't known in 1940. It couldn't be measured. The techniques weren't available. It was only measured in 1964. Another thing that he thought, and this time incorrectly as far as the Big Bang was concerned, was that it was capable of describing the production of all the elements, all the way from hydrogen and helium, all the way through to the heaviest, such as uranium. Now, we now know that's wrong. We now know that the light elements were produced, but that the heavy elements are produced in stars and not in the Big Bang.
Well, of course, we've come on now to 1948, don't we, and the first steady-state theory ideas by Hoyle, Bondi and Gould, and that caused a tremendous amount of argument. Actually, Hoyle, Bondi and Gould put forward an entirely new theory, and they did away with the Big Bang altogether. And they assume that the universe has always existed and will exist forever, and that as old galaxies pass over the boundary of the observable universe, new ones are created, very slowly of course, by material which appears spontaneously out of nothingness. So the universe is in a steady state. If we could come back in millions and millions of years, we'd still see the same numbers of galaxies as we do today. They wouldn't be the same galaxies, but they would be the same numbers of them. But that you can check, because if you look out into space, you're seeing objects which are thousands of millions of light years away. And therefore we're seeing them as they used to be thousands of millions of years ago when the universe was young. In effect, we're looking backwards in time. Now, on the steady-state theory, the distribution of the galaxies in those far-off days would be exactly the same as it is in the areas closer to us, which we see in a much more recent stage. And yet there are differences. The distribution is not the same. And that does seem to show, without any shadow of a doubt, that the steady-state theory is wrong because the universe simply is not in a steady state. And I think that most people have now abandoned that theory anyway, John.
Yes, the steady-state theory is really only of historical interest. But at the same time as that theory, as the controversy, steady-state Big Bang, was at its height, very serious work was being done by a group of combined astrophysicists and nuclear physicists explaining how in detail elements are cooked in the stars. A very famous seminal paper by the Burbages, Fowler and Hoyle accounted for most of what we know now about the way the heavier elements are produced in various kinds of stars.
Well, they certainly were looking for a Big Bang, but that founded, too, didn't it, on one rather important substance, deuterium, this form of heavy hydrogen, which is not actually created inside stars, and in fact stars actually destroy deuterium. So on that theory, there shouldn't be much deuterium around now.
That's right. If all the elements were produced in stars, there wouldn't be much deuterium. But deuterium has been widely observed nowadays all over the galaxy in the interstellar medium. It can't be produced in stars, so the stars can't account for all the elements.
And once again, I think back to the Big Bang.
There seems to be relatively little alternative to explain what we now know to be the abundances of deuterium, of helium, and of other elements, such as lithium. Now, those models which explain exactly in detail how those light elements are produced need, to understand them properly, the knowledge of three parameters of the universe, three fundamental parameters. And these are the ratio of the number of light particles or photons to ordinary matter particles or baryons. That ratio is around about 1,000 million. In fact, it's more than 1,000 million. A second parameter is the half-life, the decay lifetime of the neutron. We normally think of neutrons as stable. So they are when they're in nuclei, but free, they decay rather quickly, in something like 10.5 minutes. When they decay into protons and electrons. This lifetime can be measured, and it turns out to be a key parameter telling us how the universe behaved at an early epoch. A third parameter is the number of different types of those rather elusive particles called neutrinos. The number of different types of neutrinos. Those neutrinos are particles which have no electric charge and no mass, or perhaps a very little mass.
I remember a little while ago going to a home state mine in South Dakota, where Ray Davis is trying to catch neutrinos from the sun in a tank of cleaning fluid a mile below the Earth, and that's quite fascinating.
Yes, the neutrinos often seem to be doing their very best deliberately to avoid detection.
They do indeed.
Now, the way that these studies are linked up is interesting. From measurements of primordial lithium, how much lithium was produced in the Big Bang, we can directly infer the ratio of light particles to matter particles, that number. And that's a key thing we can derive. And in fact, it indirectly tells us the density of the universe. From the nuclear physicist, we get the half-life of the neutron. And then back again to astrophysicists, they give us this 24% excess helium, which must again have been produced in the Big Bang. Taking all these things together, we put them together, we make a model, and that predicts the number of possible types of neutrinos that there are in the universe. And that number at the moment, well, it's an upper limit, it's 4. In other words, there can't be more than 4 different types of neutrinos. Well, the astronomical measurements, even the laboratory measurements of the neutron lifetime, are not that precise. When they are refined, it's possible that those limits will come down to 3, perhaps, or even 2. Now, if they actually came down to 2, that would be rather interesting, because particle physicists know and have identified already 3 types. So if the theory says 2 and the experiments say 3, there would be a clash.
Something wrong.
That thing could be explained in terms of the fact that one of the 3 has a mass, because what the theory says isn't the number of types, it's the number of types which are massless. So the discrepancy would mean that one of them would have a mass. Now, all this is a little bit jumping ahead of the gun, jumping the gun a bit, because really the limit isn't 3 or 2, it is in fact 4. And things may be all right anyway, it may in fact never go below 3. A further thing of interest is that in a recent experiment at CERN, a brilliant experiment in which 2 new particles were found, a byproduct, a side product of that experiment was another upper limit to this number of neutrinos in the universe. That upper limit was around about 18, much broader, much less fine than the astronomical limit. Now what this means is, at this point, it's the poor man's accelerator, which is a better tool than the real accelerator, just for this particular measurement anyway.
So what you're really doing is to compare the very great with the very small. You're comparing the numbers of matter particles with the light particles or photons, and also investigating the structure and behavior of these rather strange neutrons and neutrinos.
Yes, this fascinating juxtaposition of the very big and the very small is one of the most exciting areas in all astrophysics today. But also fascinating for the astronomer is the method of making the observations. In order to understand the proportions of the light elements in the universe, we have to get ultraviolet data from the IUE satellite. We have to get optical data from a telescope that is on top of Mauna Kea, the so-called infrared mountain in Hawaii.
Yes, I know.
We have to get radio data from the enormous VLA, Very Large Array Radio Telescope in New Mexico. Combining them all together, we can learn what the true proportions of the lithium and so on were coming out of the Big Bang.
And of course, you're also looking at the very oldest stars, aren't you?
Yes, the way to find out how many elements, how the proportions went in the Big Bang, is to look back to the oldest stars in the galaxy, which were uncontaminated by things that have happened since then.
Well, it all seems fairly conclusive. But, John, we're in a fairly early stage. Do you think there's any chance of a fundamental change of outlook about all this?
Well, I think it's quite clear that in physics there is always scope for fundamental change.
Indeed.
And there are two different ideas which may come to threaten the simple, elegant idea of the Big Bang as we know it. One of them is the idea of so-called population 3 objects. These are postulated supermassive stars which might have existed before the galaxies and which are capable, in principle, of producing the lithium, the deuterium, and the helium instead of the Big Bang. They also might give rise to the cosmic background radiation. They would have to do it if they were going to be used as an alternative explanation. Personally, I think that the evidence tends to be against those models. Nevertheless, they do exist and they are quite realistic and people are trying to refine them. An entirely different kind of models is a kind of multiplicity of Big Bangs. Well, one should be more precise. There's a series of model universes called inflationary universes. And these are detailed and refined models of what went on at the very, very early epoch of the Big Bang. I can't explain them in any detail now, but one possible aspect is that we may be living in a single bubble, and there may be many, many, many bubbles, coeval, coterminous universes, many Big Bangs. However, that's very speculative, even bewildering, and I think probably this is a good place to leave the discussion.
I think it probably is. Well, John, thank you very much. Because we've got a long way. But of course, there is one point to bear in mind. We're talking about the evolution of the universe, but the one inescapable fact is that we exist. So do the sun, the stars, the earth, everything else. And no one has yet explained how the matter came into existence in the first place, which adds force, I think, to my own contention that we're pretty strong on detail and we're still very weak on fundamentals. But at least we are doing our best and we are finding out more all the time. And now, let's come back much nearer home. May the 30th, the eclipse of the sun, when the moon passes in front of the sun and partially blocks it out. This is only a partial eclipse, so I'm afraid you won't see the corona or the prominences, but all the same it will be well worth having a look at. And here is the timetable. The eclipse begins at 6:14 p.m. British summertime. That's at Greenwich, much the same over the rest of the country. Middle of the eclipse, 7:09, and there's a drawing of the sun as it will be then, and it ends at 8 o'clock in the evening. And certainly, by all means, have a look at it. But my old warning, please be careful. Don't stare at the sun with the naked eye, even if you're using a dark filter. If you must look, then take a very dark filter indeed, a welder's glass or something, and only look for fleeting seconds. Under no circumstances point a telescope or binoculars at the sun, eclipsed or not, even if you're using a dark filter, because if you do, you're bound to hurt your eyes. If you've got a telescope, then point it at the sun without looking through it and project the sun's image onto a card. And there you'll see the eclipse well. And it will be the last one for some time, and you may also see some sunspots, of which there have been quite a number recently. So don't forget to look at the eclipse, but please take all possible care. The sun is a very dangerous thing. And if you're going to photograph it, remember, a camera has a lens. So don't look straight at the sun through a camera lens either. It's dangerous to the eye. And then, finally, our next sky at night. Well, we've been very lucky. As I think you know, the Isaac Newton telescope on La Palma in the Canaries is now in action. We were very fortunate in being invited over to a commissioning night, and we were able to use the telescope, something that no television program has done before with a telescope of that size. We actually got back the first video color pictures from an object well beyond the solar system. And so I hope you'll join us next month for the Sky at Night for a night on the INT. And so for the moment, from John and myself, good night.